In 2019, NASA's New Horizons spacecraft journeyed through the Kuiper Belt, a dark patch of space at the edge of the solar system. The Kuiper Belt is filled with chunks of rock and ice, relics from the formation of the solar system. New Horizons' mission? To help us understand how planets form by taking the first ever photos of an ancient and mysterious rock called Arrokoth, or to the scientists, MU-69.
So New Horizons flew by this very distant, cold Kuiper Belt object in January 2019. And the reason that that was important was because what we're looking at is truly the first primordial remnant of solar system formation that we've ever seen. This was the first time we'd ever really seen a building block of a planet.
This grainy image shows a weird 22-mile-long rock. It looks like a pair of planetesimals stuck together with glue. The photo reveals a missing stage of planet formation.
What this is telling us is that you don't always just get two objects smashing into each other. They can actually very gently coalesce. And this tells us a lot about how smaller objects aggregate to form bigger ones.
MU-69 formed 4.5 billion years ago when the gravity of two planetesimals pulled them together.
Two separate bodies were orbiting each other and ended up getting kind of pushed together at really low velocity and just stuck the head right on the shoulders.
And there's also friction that as they brushed against each other, the ice that they're made from, that energy would have melted them and then refroze. And so it's that combination of sort of a slow coming together, the gravity wanting to hold them together, and then the ice kind of creating that bond that was enabling them to stick together.
Bonded together by gravity and friction, the two planetesimals became MU-69, a planet-building fossil.
MU-69 is almost like the missing link. It's showing us what happened right after we went from dust and pebbles to planetesimals.
The inner region of a protoplanetary disk is a chaotic and violent place. Collisions between planetesimals are frequent. "20-mile-wide planetesimals fuse together and go on to form 1,000-mile-wide protoplanets."
As the bigger you are, the easier it is for you to grab gravitationally other objects like you around you in the neighborhood and grow even bigger.
When protoplanets form from dust, pebbles, and finally planetesimals, it's known as the core accretion model of planet building. We think this is how all planets are born. But looking around the solar system, we can see that while all planets are born equal, they grow up very differently. For instance, why are the planets in the outer solar system huge and planets closer to the sun small? Could it be because of what they ate as infants?
It really is to do with the chemistry and the physics of the solar system that gives you these very different sizes of planets in different regions.
4.5 billion years ago, the sun plays a big role in the chemistry of the infant solar system. Near the sun, temperatures are high.
It's too hot. The gas is too energetic and it escapes and you lose all that gas. So what you end up with is mainly rock and metal in the inner solar system because that's what's able to survive the early heat of the sun.
The rock and metal that survives eventually forms the terrestrial planets: Mercury, Venus, Earth, and Mars. Further from the sun, it's cooler. Around 250 million miles out, it gets so cold that we hit the frost line.
So a frost line is the point or distance from a star where you get far enough away from the star that it's so cold that water freezes and becomes solid ice as compared to gas or vapor.
Beyond this frost line, there suddenly becomes a lot more material to make planetesimals from. So there's a lot more water available, primarily in its frozen form, in the outer solar system than there is, rocky mineral and metallic matter in the inner solar system.
Beyond the frost line, the presence of water ice helps double the amount of solid planet-forming material. And these icy building blocks can bond together very easily.
With water in the equation, you now have this frosty Velcro-like surface on the planetesimals, and it's that extra stickiness, that extra grip ability that can help accelerate the accretion process.
So we can build bigger planets beyond the frost line because there's more solid material to work with, because stuff like water has turned into solids, and because that solid material is more sticky.
This extra sticky material helps build colossal planetary cores. Planets like Jupiter become gas giants.
To form a gas giant, it's simply about having a large enough core to have enough gravity to start grabbing gas and holding on to it. And that's it.
Once you've accreted a protoplanetary core that's maybe 10 or 20 Earth masses in size, you can now very rapidly start to grow much larger by drawing in the gas.
All of a sudden, things are falling in an almost uncontrolled way, a runaway gas accretion. And that's how you build a giant planet.
Core accretion should explain how all planets form. But when scientists try to apply the model to Jupiter, it doesn't work.
So if you try to build Jupiter's core, you run into a timing problem. So the time it takes to build a core big enough to form Jupiter, that might take 10 or 20 or 100 million years.
And it turns out that's too long.
As Jupiter is forming and starting to accrete all that wonderful hydrogen and helium, the sun is getting warmer and pushing all that material out of the solar system altogether. So as Jupiter's growing and feeding, it's like, hey, what are you doing to all my food?
The growing gas giant is in a race against time. The clock is ticking. The planet must fully form before its food